Hey everybody, welcome back. Time for a new unit. Gonna kind of put the wrap on our equilibrium and start to talk a little bit more about thermodynamics. So today's video is really just going to be kind of a quick review of what we had from our college chem days, just to make sure as we're kind of talking about our thermodynamics, it's bringing back some of these terms and some of the vocab that we've seen in our previous unit from college chem, as well as introduce kind of one new term when we start to describe and kind of the whole reason we're doing thermodynamics, and that is our spontaneity. But hold that thought. Let's do a little review. So hopefully you are reminded of our first law of thermodynamics. We talked about this quite a bit in our college chem. First law of thermodynamics says that energy cannot be created or destroyed. There's a law of conservation of energy. That means if it goes from somewhere, it must come from someplace else. When we start to kind of define our systems versus our surroundings in terms of where our energy is actually coming from or going to. Remember that your system, the thing we're in chemistry gonna always be interested in, your system is always going to be the chemicals, the bonds that are breaking and forming. The surroundings is going to be everything else around it. Surroundings usually will always involve as well your thermometer. It's always just kind of recording the temperature change, not actively participating in it, as well as usually an aqueous medium. Your water is typically, not always, but typically also part of your surroundings as an additional kind of vessel to absorb or release heat into the bonds as is necessary. Cool. Quick review. First law of thermodynamics. State functions. Reminder that our state functions are functions that are independent of the pathway. It does not matter how you did the change or the steps that it took. It is just the difference of the final and the initial for that change in total value. That's your capital letters. Remember that energy and enthalpy, H, are state functions. The total change in heat energy, that's your enthalpy. It doesn't matter how many steps you took to get there. It's always kind of the difference of where you started versus where you ended. Q, however, your heat gained or lost, is pathway dependent, as is your work. The path that you took does depend on kind of the amount of energy required to get there. So, boop, energy change, enthalpy change, state functions, capital letters, Q and W, your heat and your work are not state functions. Reminder, we can actually calculate the change in internal energy. That's your delta U here. Your change in internal energy of your system is always a function of the heat and the work done on or by the system. And I believe we're a little different than our physics. If you've seen this in your physics, I think there's a sign connotation here. And that's because of the way we're focusing. We're looking at specifically the reaction. Everything we're interested in is what's happening to the energy of the chemicals. Physics wants to know what we can do with said work. And so that's where the signs change a little different. But for us, Q plus W equals the change in internal energy. Reminder, if heat is lost, Q is negative. If heat is gained by the reactants and or the system, Q is positive value. We're adding that heat energy in, or endothermic, endo coming in. Remember that if your system is being worked on, your work is positive. That's energy being added to the system. If your system is doing work on the surroundings, we'd say it's a negative work value. It's losing energy because usually it's pushing a cylinder or pushing gas particles out of the way. Just think about some of our signs from our Chem 1 content, by which I mean our college chemistry. Sorry. Cool. Remember delta H, this is the heat transferred at constant pressure. If you remember, there's a derivation that lets us go from Q to delta H if the pressure remains the same. Here in the lab, our pressure is almost always going to be constant. So we can actually start to say that Q and delta H are kind of the same thing for a chemical reaction, so long as our pressure is held constant. Remember that for an exothermic process, delta H is negative because we're losing that heat energy going out of the reactants and products leaving the chemical system. For an endothermic process, delta H is greater than 0, or is a positive value in terms of how we start to see the change in energies of our reactants versus products. Throw back here, but good to review it. Q, cool. A couple other things to be reminded of. Q is your heat gained or lost. from a chemical reaction. Q equals mc delta T. This was your calorimetry, where M is the mass, C is the specific heat of the substance transferring that heat energy, delta T being the change in the temperature. And so we can use that to actually quantify the amount of heat energy being gained or lost. And then if the pressure is constant, that Q will also be the H, which is super handy when we start to actually gather this data in the lab. A reminder on Hess's law. Hess's law says that if you want to know the change in your delta H overall, your total change for our chemical reaction, we can actually take steps, take individual reactants, individual chemical reactions, and add them together. And the enthalpy change of the overall process is the sum of the enthalpy changes of its individual steps. That we can actually add up all of the individual steps, add them all together. And if we do that, we can actually solve for the change in enthalpy directly because it's a state function, which is super nice. This lets us solve for chemical reactions that might be hard to measure directly. Maybe they're too fast, or maybe they happen in a gaseous atmosphere that are harder to actually be able to take the temperature of. Whereas now we can look at multiple steps, add them all together. A quick review of that math. Sorry, this last one here should say overall. So that last line, delta H3 is your overall reaction. Could we go from reaction 1 and 2 to our overall? Well, sure. Just a reminder that your delta H is dependent on your coefficients, your stoichiometric amounts, which means whatever you do to your coefficients, you also do to your delta H. For example, if we were to flip the first reaction, I don't know if we need to here or not, but if we were to flip the first reaction, we know that as written, sulfur and oxygen will join together to release this much heat energy, right? Exothermic, because it's a negative delta H. But if we were to flip it, if we were to write it as SO2 decomposing into sulfur and oxygen, well, that would be the same amount of energy. It's just we'd have to put it in. The signs would flip on your delta H. Quick review here. So it'd become a positive value. I don't know if we got to do that. It's just worth kind of talking about when we start to look at these reactions. We got to get 1 and 2 to add together to make 3. 1 plus 2 equals 3. Looks like we've got an intermediate here. We got this SO2 and this SO2. Problem is we got 2 in reaction 2, but only 1 in reaction 1. So I think we're going to have to divide everything in reaction 2 by 2, right? So I divide by, or multiply by 1/2, however you want to think about that. I'm going to divide by 2. 1 divided by 2 is 1/2. 2 divided by 2. Cool. So essentially these cancel out. If I divided everything here by 2, I would also divide this by 2, this term by 2. Cool. Now if I'm thinking about my intermediates, if I were to add them together just as I have them written, I got an SO2 here and SO2 here, opposite sides cancel. I got an O2 on the first reaction. That's the same as a 2 over 2 if I want to get my denominators the same to add them. So I've got an S, 2 over 2 plus 1 over 2 is 3/2. Yeah, so those work. And we've got SO3. So as written, we can just add these together. We would do the same for our delta H. We would add those together to get our delta H3. Cool, just a quick refresher on our Hess's law as we start to think about how we can solve for our overall heat of our reaction. And all that brings us to our spontaneity, how we can start to think about whether or not a reaction is spontaneous. Well, what does that mean? What does that mean if something is spontaneous? Well, we spent a lot of time looking at rates and our kinetics, and they tell us how quickly the rate or the speed at which the reaction is going to go. Thermodynamics, our new chapter here, is going to tell us whether or not we're going to be spontaneous, whether the reaction as we are seeing it or as is written is actually going to want to go all on its own. So chemical thermodynamics provides us information about our equilibrium and whether or not that equilibrium, which we know it wants to get to, right? We always try to get to equilibrium, whether or not that change is spontaneous. And you've heard this term before, right? Spontaneous. For example, like spontaneous combustion, right? And so when we're thinking about our energy diagrams, we know we can kind of, if we're doing our reaction progress versus our change in energy, this would be for an exothermic process where our reactants had more energy. We lost some energy to the surroundings and now our final products have less energy. The difference in our energies here, well, that's the thermodynamics. We're actually becoming more stable, releasing heat energy. Exothermic reactions tend to be spontaneous. More on that to come. The kinetics is how easily or how quickly we get there. And that's that activation energy. Oh, throw back to chapter 16. The bigger this hurdle, the harder or the longer it's going to take to get our products to actually change. So when we think about things like diamond, right? Diamond is thermodynamically favored to change into graphite. It would actually have less internal energy if it turned into our graphite, our final products. That would be an exothermic process. But because of how strongly attracted they are to one another, the amount of energy, that activation energy that we would have to put in to get it to change is so high that it's not kinetically favored. And this is why our diamonds don't spontaneously turn into graphite. It's because the amount of activation energy necessary to get that to go is so very high. Paper, on the other hand, burns. The second you kind of light it with a fuel source or a ignition source, a spark or a flame, that paper starts to burn almost immediately. That process is both kinetically and product favored. It wants to burn. That is a spontaneous process. It goes all on its own once you get it started. And that's where it can be a little tricky when we start to look at these reactions. So what do we mean when we say a spontaneous process? A spontaneous process is a change, both physical or chemical, that happens all by itself under specific conditions without any ongoing input or outside energy acting upon it. Once it starts to happen, it goes all by itself. We don't have to interact with it anymore. We don't have to change anything. It will go all by itself. Example of a physical process or a push, if you will. So some chemical reactions, you got to get the reaction started, kind of like thermite, right? We saw that one, had to get over that initial kind of ignition. But once it started, it had enough energy to keep going all on its own. If you had a book on a desk and you give it a little push, yeah, a little activation energy, but it then falls all by itself. You don't have to push it all the way down to the floor. That is still a spontaneous process. And what's nice is, going to get a little further along here, by looking at a couple of our kind of conditions, we can start to say then for a chemical reaction, is this process going to be spontaneous or not? Will, as we have it written under these conditions, will it go or not? And if it doesn't go, what do I have to change to get it to go? Again, a lot of what we talked about in chemistry is this control idea, right? How can I make more products? How can I make it happen faster? Now, how can I make it go all on its own? And that's kind of our next piece of the puzzle that we're adding in here now that we're talking about our spontaneity or spontaneous reactions. Cool. More on this to come. Just want to kind of get you started on our chemical reactions.